In this video, I'm going to talk about acceleration versus time graphs. Acceleration versus time, and these are really simple, right? Really simple because when we had position versus time, slope represented velocity, and when we had velocity versus time, slope represented acceleration. In an acceleration versus time graph, slope actually doesn't represent anything. Okay, at least not in this class. Not that we're learning today. So that's why these tend to be pretty easy. This is going to be a quick video. All this is going to be is a graph that looks like this. You still have positive and negative values, positive on the top, negative on the bottom. Acceleration graphed on the y-axis, time on the x. And motion that looks like this. This would be positive constant acceleration. So this would be the rope that's pulling to the right, and it doesn't change in the rate of acceleration. And if we had a line that looked like this, that would be negative constant acceleration. That would be the rope pulling to the left at a constant rate. In this class, regular physics, all we're going to have is constant acceleration. We'll never have changing acceleration like a slanted line. That's never going to happen in this course. So to talk about these motion graphs kind of all together and include acceleration versus time graphs, I want to look at these problems here. And this is courtesy of Dean Baird, Book of Phys. Thank you. But let's look at the problems that he's put up for us. This is a position time graph. This is a velocity time graph, acceleration time. What I want to do here is I want to depict the same motion on all three graphs and consider what it would look like. To do that, I want to consider what I have here in the first graph. This is a position time graph. Remember that when we look at a position time graph, slope is velocity. This slope is positive, therefore I know that this velocity is positive. The slope is also unchanging, it's constant. So I know that velocity in this motion, there is some positive constant velocity. So the question is, how do I graph positive constant velocity on a velocity time graph? Well, if it's positive velocities are found above the x-axis. And if it's constant, that means velocity doesn't change. And if velocities are the y values, that means the y value doesn't change. So we'll end up with a straight line across that looks like this. Positive, constant velocity. And then we ask ourselves a question, is this object accelerating? Well, no, it can't be accelerating because it's not changing velocity. So the acceleration would be 0. That's why we have this line down here. Also, we should know that slope is acceleration here, and this slope is 0, therefore acceleration is 0. I want you to think about something also as we move this way. For instance, as we go from a position versus time graph to a velocity versus time graph, we gain some information about this motion. We gain information about acceleration. I didn't know anything about acceleration up here. I can tell if the object is accelerating or not based on whether velocity is constant, but I couldn't actually calculate the acceleration. Now I can calculate it here. But I also lose some information. So I gain information about acceleration, but I am also going to lose some information when I go to a velocity time graph. The information I lose is information about position. I knew where the object was in this graph. Here, I do not know where the object is. I don't know the position of the object. I can have a positive velocity and have a negative or positive position. So I lose some information about position. Let's look at number 2. Let's consider this one. This is positively sloped on a position time graph, therefore I know velocity is positive. And the slope isn't changing, therefore I know that the velocity is constant. And so I'm going to graph that on the velocity time graph. How do I graph positive constant velocity? Well, we just did that here. Positive constant velocity is a straight line all the way across for the same reason. And the next question, is this object accelerating? Well, no, acceleration equals 0 because the slope equals 0. And so if acceleration is 0, there we go. Acceleration is 0. So notice that these two graphs are the same. These two graphs are the same. Even though we have a different motion, this highlights the fact that we have lost information about position with velocity versus time. Because the only thing that's changed between this motion and this motion is the position. Well, we can't tell what the position is. That's why the graph looks the same. Look at number 3. Negatively sloped, therefore the velocity is negative. We're moving backwards. Slope still doesn't change, so we know it's constant. How do we graph constant negative velocity? Well, constant velocity is still going to be a line that goes straight across because we know the y value can't change. Negative velocities will be negative y values underneath the x-axis. So this one is going to look like this. The whole time constant velocity, the whole time negatively sloped, and that's what we end up with. So the same question, what's the slope of this graph and what does it represent? Well, slope is 0, and if the slope represents acceleration, that means acceleration is 0. How do I graph 0 acceleration? There we go. So notice these 3 graphs were the same, even though we have 3 different motions. Basically what that means is that this acceleration time graph is probably the least useful of the motion graphs that we'll have. The velocity time graph is going to be the most useful. We like it. It's also maybe the most complicated to analyze as well. Lastly, let's look at graph number 4. This one looks like we have a little bit of a kink in our motion here, so let's analyze it. In this first part of the graph, this line is positively sloped, so that means our velocity is positive. Then we change here to a negative slope, that means velocity is negative. So we go forward and then we go backward. But in both of these instances, the velocity is constant. We don't have a curvy line. So we have constant speed here, constant speed here. The only time we have acceleration or changing speed is right here at this point. That's instantaneous change in speed. To change speed, you have to have acceleration, and we'll talk about that in later lectures. But for right now, we're going to consider these to be constant speed. So for this first part of the graph, how do I graph positive, constant velocity? Well, positive velocity is up here. Constant has to be straight across, so it's going to look like this. And now we have negative constant velocity on this part of the graph. Negative values are below the x-axis. Constant velocity must go straight across because the y value doesn't change. There's not a line in between here because if there was, this wouldn't really be a function. It wouldn't pass the vertical line test. So I'm just going to leave it like this. And the question is, are we accelerating? What's the slope of these two lines? Well, the slope of both of these lines is still 0. Therefore, the acceleration is still 0. Still straight across. Technically, again, we are accelerating at this point, so there should be some spike up to infinity, perhaps. Well, not infinity. There would be some spike up here to show that there's acceleration. But for now, I'm not going to worry about that. I'm just going to highlight the fact that our speed, at least in each section, is not changing. Still 0 acceleration. So again, check it out that we got same acceleration graph all 4 times, despite the fact that we had different motions. Once again, highlighting the fact that the acceleration time graph probably not the most useful for us to use.